We're going to continue where we left off yesterday, and we're looking at these 4 basic questions in any multiple linear regression model. Let's do the questions again, and the questions are: is at least one of the predictors x1 to xp useful in predicting the response? This means within a specific confidence interval, 90%, 95%, can we reject the null hypothesis that the beta, the true slope parameter is 0, at least for one predictor, at least for one? Second question is, do all the predictors help to explain why? Or is only a subset of the predictors useful? Can we do away with some of the predictors? How well does the model fit the data? And finally, given a set of predictor values, what response value should we predict? And how accurate is our prediction? Let's start with the first one. Recall that in the simple linear regression setting, in order to determine whether there is a relationship between the response and the predictor, we can simply check whether the true value of beta 1 is equal to 0. In the multiple regression setting with p predictors, we need to ask whether all of the regression coefficients are 0. That is, whether beta 1 is equal to beta 2 is equal to, all the way to beta p, all of them equal to 0. As in the simple linear regression setting, we use a hypothesis test to answer this question. We test the null hypothesis, H0, is that all the betas are 0 versus the alternative, and that would mean that there is, at the very least, one of these betas, so beta j, is non-zero. This hypothesis test is performed by computing the F-Statistic. We're no longer using a T distribution. This instead, for reasons that the book, I would imagine, definitely doesn't go into, but it's an F distribution. We ran a couple of simulations yesterday with the F distribution. It has 2 parameters, degree of freedom 1 and degree of freedom 2. What's the calculation? It is the difference between, we just have to double check what TSS refers to. It's defined in the previous pages. The difference between TSS minus RSS scaled by P divided by RSS scaled by N minus P minus 1. What would be interesting is if P was 1, which would be like the linear regression, do we retrieve the calculation in the case where there's only one predictor? Would be interesting to see if what we did in linear regression, in simple linear regression with the T statistic, if it's a special case of this calculation over here. Where, as with simple linear regression, the TSS is defined as follows. So you're looking at kind of how far the Y observation data is from the mean of Y, squared summed over the total number of observations. RSS is what we've mentioned practically every session these past few days, where you're taking the difference of yi and yi hat, again squared and summed. if the linear model assumptions are correct, one can show that, and I think this E means the expectation, what you would expect. That you would expect, so pick a random data set, and on average, you would expect that dividing the RSS by this denominator is equal to sigma squared. Let's remind ourselves, sigma is the standard deviation of the error term of epsilon. And that provided H naught is true, so only if H naught is true, then the expectation of this is equal to sigma squared. Let's just take the book on its word. This is probably quite an easy way of deriving these. And then notice they are the numerator and the denominator of this calculation over here. So you would always expect that the expectation of the numerator is equal to sigma squared. If H naught is true, now we're going to the denominator. If H naught is true, if there is no relationship between the response variable y and any or all, if there's no relationship between y and any of the xi's, then the denominator is also expected on average to give you sigma squared. So dividing these two would give you 1 if H naught is true. Hence, when there is no relationship between the response and predictors, one would expect the F-statistic to take on a value close to 1. On the other hand, if HA is true, then the expectation of the denominator is greater than sigma squared, so we expect F naught. Or is this the numerator? Excuse me, I think I muddled them up, right? Yeah, this one is the numerator, in fact. You would expect the numerator to be greater than sigma squared. So we expect F to be greater than 1. Might be a good time to go into our studio and just have a look at these things, but let's just continue reading for the time being. The F-statistic, the multiple linear regression model obtained by regressing sales onto these 3 predictor variables, radio, TV, and newspaper, is shown in table 3.6. This is the F-statistic as calculated using this formula. So just take your random, I should say residual sum of squares, calculate your TSS. Don't ask me what that stands for on this, unless you'd like me to very quickly look it up. The TSS was the total sum of squares. So take your difference between your total sum of squares and your residual sum of squares. By the way, your total sum of squares does not depend on the model. Notice that in the formula there are no hats. It is the residual sum of squares where you get a hat, and that hat depends on the model that you have fitted, the model that you're using, that you're testing, that you're for which that you're producing these diagnostics. The F-statistic is 570. So it looks larger than 1, but what does that mean? Is 570 significantly, is it statistically significantly larger than 1? This is where you use the F distribution. But I think the book is, for the time being, is content with just saying this is far larger, in inverted commas, whatever we mean by far larger. It's larger. I mean, 570 is larger than 1. Is it far larger than 1? Well, that would be relative to your confidence interval. If you're working at a 99.9999999% confidence interval, maybe we wouldn't consider 570 to be significantly larger than 1. It is all relative. However, reading on, since this is far larger than 1, it provides compelling evidence against the null hypothesis. This is where we would say we reject the null hypothesis. In other words, the large F statistic suggests that at least one of the advertising media must be related to sales. However, what if the F statistic had been closer to 1? How large does the F statistic need to be before we can reject H0? And exactly right, how large does the F statistic need to be before we can reject H0 and conclude that there is a relationship? That would be the alternative hypothesis. It turns out that the answer depends on the values of the number of observations n and the number of predictor variables p. When n is large, an F statistic that is just a little larger than 1 might still provide evidence against H0. In contrast, a larger F statistic is needed to reject H0 if n is small. We're looking at sample sizes right over here. The more data you're allowing for, the larger your data set is, means that you're considering more of the different possibilities. And as a result, you don't need, the larger n is, that would mean that you don't need such a large F statistic to reject the null hypothesis. In contrast, a larger F statistic is needed to reject H0 if n is small. When H0 is true and the errors epsilon I have a normal distribution, the F statistic follows what we call an F distribution. And I haven't even started RStudio, but it's probably a really good idea. It takes some time to load, but we'll look at this F distribution, and let's emphasize it. Emphasize it over here. So given certain assumptions, and the assumptions are that H0 is true, as well as the errors have a normal distribution, then the F statistic should follow an F distribution. It's the entire reason why we're referring to it as an F statistic. Let's go into RStudio, and we'll just take the script over here. How do you generate like this? And let's generate 1,000 of them. And are the degrees of freedom going to be the n and the p, I wonder? I wish it uses some specific values. We might have to wait for the lab section. If we go to the section where they're actually using R code, which is actually quite far off. Might be one of the longer chapters, but here we go, right? In interaction terms, this is all R now. So look, multiple linear regression. And look, interesting. The LM is also giving you, why didn't we have this in our previous code? Where it's calculating these t statistics. Do you need to type summary? So when we had, going back to R, going back to what we did a couple of sessions ago, where we had all these different data sets, right? Did I change the slope to 0? Yeah, I've changed the slope to 0. If we take LM, which is fitting the linear model, and we do it, for example, for the 50th data set, which would be K is just the kth data set. And we call it, for example, 50th data set. This is our intercept, this is our slope, quite close to 0. If I now type summary, 50th data set. Oh, interesting. Interesting. Look. It gives you the residuals. So the worst fit is over here. It's one specific data point. Let me just, which is the 50th data set. 50th data set will be this one. So the LM function is passing a line, is drawing a line. I actually think there's a way of doing it. There might be a way of doing it. I'm not entirely hopeful, but is it abline? Abline. Oh, look, it worked. So it's passing this line, which it's interesting. Is it really this line that? So the rest don't have it, but this one has it, because we're working just on the 50th data set. It's giving a y-intercept of 5, as you would expect, just because this is what I've started out with. A true intercept of 5 and a true slope of 0. And look. The t statistic is quite close to 0. In fact, it has a p-value of around 75%. So you would reject, you would not reject the hypothesis. What is the hypothesis? That there's actually no relationship between the predictor variable, your input variable, and the response variable y. On the other hand, over here, this is so small. This is so small. In fact, you see these asterisks, that's when it's significant. This means very significant, relatively significant, less significant, and this is what we have. We have nothing. We have nothing. There aren't any stars. There isn't a dot. When you have nothing, it means there is no significance. There's no significance. And we have a couple of other diagnostics. We have the p-value for the slope, which is the same thing as over here. 98 degrees of freedom. That just means 100 observations minus 2. You might remember subtracting 2 in the calculation of the SE, the residual square error, or should I say the residual standard error? That would look like it, right? The residual standard error. This is to approximate the standard deviation within the error term. And in fact, it does quite a good job because the true standard deviation is 3. And what we have over here is, you know, to one significant figure, it is in fact 3. Now, can we do an F-test? Let's see. So why is it still calculating? Oh, look, an F-statistic. An F-statistic, and there is the p-value. So it's so small that you reject the null hypothesis. But maybe I'm getting slightly should we go back over here? So this is how we're going to answer the first question. Is at least one of the predictors useful in predicting the response? We're going to perform this calculation. The higher it is, the more likely we are to reject the null hypothesis and sort of conclude that there is, yes, at least one predictor variable. There's one predictor variable that influences the values of the response variables. Variable singular. We're only modeling one output variable. Okay. Based on this p-value, the p-value is calculated using the F distribution. Let's have a look at the F distribution. Now, which parameters to take? Unfortunately, if the book is telling us which parameters, I think it's just these two: the n and the number of predictor variables. So let's see. What if I simulate 10,000 and I say the first degree of freedom is the 200 observations, and the second degree of freedom is the 3 predictor variables. Okay, and I'll do summary. Let's call this, I don't know, generated. And now we can say generated. Look, we have for 200 observations and 3 random and 3 predictor variables, x1, x2, x3. The greatest generated value is 439, and we got 570, which is larger than 439. This is a histogram. It doesn't look right, does it? Unless we need to change the scale. I see. Let's try breaks. So 100. Oh, okay. Look. Oh, right. So most of the data, 75% of the data, only gets until 2.47, whereas this 439 is really far out. It's very unlikely to get anything this high. Most of the data is clustered. They're definitely up to 75% of the generated data values are less than or equal to 2.4798. So we can say with some confidence that this 570 is a really high value it's really unlikely that the 570 is just generated by random chance. So we reject the null hypothesis. So for the advertising data, the p-value associated with the F-statistic in table 3.6 is essentially 0. And the lower the p-value, the more likely you are to reject the null hypothesis. So we have extremely strong evidence that at least one of the media is associated with increased sales. In 3.23, and what is 3.23? This. In 3.23, we are testing H0 that all the coefficients are 0. Sometimes we want to test that a particular subset. So are we answering the second question now, perhaps? Or is only a subset of the predictors useful? So you shall take a subset. Sometimes we want to test that a particular subset of Q of the coefficients are 0. So am I understanding the indexation? Are we leaving the first Q? I think we're leaving the first Q out. So then it starts from P minus Q plus 1, P minus Q plus 2, until P. Where for convenience, we have put the variables chosen for omission at the end of the list. At the end of the list. Let's have a look. So I think we're going to have to read this a second time. In 3.23, we are testing H0 that all the coefficients are 0. Sometimes we want to test that a particular subset of Q. Okay. So you're looking at so are there Q of these? Yeah, I think so, right? I think it's very easy to see. So if we had, for example, 5th to 6th, 5th to 11th, that's how many items. Well, the formula is, and a lot of you, if you're not careful, your brain might try convincing you it's 11 minus 5. It's always 11 minus 5 plus 1. You can try this by counting on your fingers. So there are actually 7 of them. 5th, 6th, 7th, 8th, 9th, 10th, 11th. Same thing over here. So we have the P minus Q plus 1 until the Pth. So we say P minus Q plus 1, and then I need to add the 1, just like earlier. And what do we get? P minus P is 0, negative Q is Q, and -1 plus 1 is 0. And that's exactly it. So we're only looking at Q predictor variables. In total, at least the data set that's available to us, we have P, and we're taking P as greater than or equal to Q. You might only want to look at Q of them. I wonder if you could take only one. Can we take Q as 1? That would be interesting. Now we'll see. In this case, we fit a second model that uses all the variables except those last Q. Suppose that the residual sum of squares for that model is RSS naught. So this is our second model. Then the appropriate F-statistic is this one over here. Interesting. So we've replaced the total sum of squares. You might have to put them side by side. What's interesting is that these two p's, only one of them has changed. I'm going to skip this just because I'm not operating at 100% today. I actually had quite an engaging debate earlier with one of the actuarial societies. Let's have a look. Let's at least introduce ourselves to question 2, which is deciding on important variables. As discussed in the previous section, the first step in a multiple regression analysis is to compute the F-statistic and to examine the associated p-value. If we conclude on the basis that of that p-value that at least one of the predictors is related to the response, then it is natural to wonder which are the guilty ones. We could look at the individual p-values as in table 3.4. So this is your table 3.4. We look at the individual p-values. So this would appear to suggest that we can exclude newspaper, and we're left with TV and radio. We could look at the individual p-values as in table 3.4, but as discussed, if p is large, we are likely to make some false discoveries. It is possible that all of the predictors are associated with the response, but it is more often the case that the response is only related to a subset of the predictors. The task of determining which predictors are associated with the response in order to fit a single model involving only those predictors is referred to as variable selection. The variable selection problem is studied extensively in chapter 6. And so here we will provide only a brief outline of some classical approaches. Ideally, we would like to perform variable selection by trying out a lot of different models, each containing a different subset of the predictors. For instance, if P is 2, then we can consider 4 models. A model containing no variables, a model containing x1 only, a model containing x2 only, a model containing both x1 and x2. And the thing is, this grows exponentially large very quickly. So it is either include or exclude. So if you had 3 of them, if there were 3 predictor variables, that would increase to 8, because each predictor variable you include or you exclude. So it would be would it be 2 cubed? I think it would be 2 cubed. How do we determine which model is best? Various statistics can be used to judge the quality of a model. And these are new statistics again. So we had our T statistic, our F statistic. Now we have Mallow's CP. Never worked with it. How do I pronounce this name? This is very, very important. I think it's a khaki information criterion. best known in its abbreviated form, the AIC, and as well as these last two, Bayesian information criterion and adjusted R-squared. Having said this, look, look how it grows exponentially. They're taking the example, if your data set has 30 possible predictor variables that you may choose to include in your model, it's very difficult to do this in a brute force way. Brute force meaning first trying to model with just one of them, and then trying with another one, or with two of them, or with three of them. If you have 30 and you wanted to try each possible combination, and what do I mean by combination? Which variables to include, which variables to exclude. You include half, exclude the other half. Well, you would get, is that over 1 billion? You very quickly get many different configurations, which, well, it's just not feasible to try each one. So this is why we have these statistics. Unfortunately, there are a total of 2 to the power of p models that contain subsets of p variables. This means that even for moderate p, trying out every possible subset of the predictors is infeasible. For instance, we saw that if p is 2, that's quite manageable, isn't it? Getting to p equals 30, we must then consider these more than 1 billion models. Clearly, this is not practical. Therefore, unless p is very small, we cannot consider all 2 to the power of p models, and instead we need an automated and efficient approach to choose a smaller set of models to consider. There seem to be 3 classical approaches, and I'm expecting that we're going to build on these in chapter 6. Forward selection, backward selection, and what might be a mix, a combination of forward and backward. Tomorrow, we'll look at the 3rd question, which is how accurate the model fit is, and final question, how to actually perform predictions. I would expect this to be the easiest section. We'll then have the opportunity to consider qualitative predictors where we're not measuring numerically. This is going to look nice. And maybe we get more into linear regression, but with qualitative data. Looks like fun, but we'll end it over here.